In this video, I'd like to introduce the OIM Analysis software package. OIM Analysis is the software used to visualize and analyze the orientation data that's been collected in the APEX software. This is shown schematically here, where the orientation data is basically collected at each point on a measurement grid. And from this data, we can generate different types of maps. We can generate charts showing the distributions of quantitative measurements. And we can generate plots and texture plots to look at the orientation distributions from the measured microstructure. This is a screenshot of the user interface for OIM Analysis. I'd like to highlight a few key features. We have our standard toolbar. This is where you have your file open. I use these a lot, where you can tile windows or close all windows. This accesses your standard your standard operational tools. We have our Quick Gen toolbar. There's a separate video specifically for this, but this gives access to the most commonly used maps, charts, and plots for a data set. There's a highlighting toolbar, which is used for interactively investigating your data through highlighting, where we can select specific regions or subsets of data and see it on correlated maps. And we have our Crystal Utilities toolbar, where we can see things like symmetric orientations, equivalent planes, and calculate crystallographic information. We also have our project tree. We have a separate video about how to operate with this project tree, but this is the tool used to organize the data as it's analyzed. You can see the different types of outputs we can get. We can get a map, a chart, a plot, and summary windows. For many of the windows, there are secondary view panels or panes here. For example, on this map, we can access the FlexiView tools. We can look at the crystal lattice. We can do interactive analysis that provides point-and-click analysis. All these maps, as they're generated, populate the project tree. And you can see that all the analyzed are organized by what we call a partition. So the default partition for the data is the all data partition, which contains all the data that's been collected. But you can see in this example here, we can create other partitions. So in this case, the other partitions are all the different phases. On this second data set down here, the dual phase titanium, you can see there's a partition for the alpha phase, the beta phase, but also a partition has been created that says the titanium alpha phase, but the small grains only. So we can use some of the tools to partition data in an array of ways to isolate the specific microstructural features of interest. If we look at this project tree to kind of see the things that are in here, again, all the documents that are created during analysis session are generated and organized in this project. We have a data set level part of the project. This is when we open a data set. This is what we see. That's the file name. And below that, we have, again, these partitions, the subset of the data that meet our described criteria. And when we do this, only the points that meet this criteria are selected for that partition. And underneath here, we can have different maps, charts, and plots. So these are an example of an auto IPF as an orientation map, different EDS maps, a combined image quality IPF map that show up under the partition of interest. This icon here shows a chart. There's things like grain size distribution, image quality distribution. For a lot of the types of maps we can display, we can see a chart that shows the distribution of those measurements. Then we have a texture, and a texture is where we are looking at the strength of a preferred orientation and distributions of preferred orientations in a material. And once we have these, we can plot out pole figures, inverse pole figures, ODFs from different textures based on these calculations. And then at the very top level, we have a function here called multi-chart. This is when we want to plot data from multiple different data sets or different partitions. We access that through the multi-chart functionality. So one thing I want to highlight here is within the software, There are different tutorials. You can access these through the help. There are things like this where there are specific step-by-step guides to walk through things. So this walks through how to open a data set. So you create a project here. You right-click on the project icon to select new data set. You browse to the data set of interest. It'll create a all data partition. You can create here. You can switch to the lattice mode after you've created a map. And then you can notice how the crystal rotates around. This is just a quick thing you can try just to get a general feel. There is a subsequent video for opening projects available in this set of videos. And then I mentioned partitioning. This is just an example, a snapshot of the partition window here. So you can see we can partition the data numerous ways, and we're basically just defining a subset. So when we do this, we have point properties and we have grain properties. And in a subsequent video, I'll describe how grains are calculated. But essentially, a point property is just based on where we're classifying individual points in the map. Grain properties, what we're doing is we're first grouping together points as grains, and then we're making decisions based on these grain properties. And so you'll see in our partition window, we can define the grain size grouping algorithm here in the grain size tab. And we'll talk about that when we have the video about grains. But this is just an example how we can use Boolean logic and set things up. So here we've defined the grain size range as less than 2.5 microns, and it's the alpha phase. So points and grains that meet that criteria would show up in this partition, and we can do analysis just based on this. Whereas the alpha grains that are greater than 2.5 microns would be defined and give us a different orientation distribution. A commonly used partition is to partition by confidence index. Confidence index is a measure of how reliable and how accurate the automated orientation solution should be. So this is an example of just all data from an aluminum film. And when we apply the confidence filter here in terms of 0.2 or greater, you can see that we're just left essentially with this fiber texture, this radially symmetric texture here. The noise through here has been eliminated. And the reason that is if we look at the distribution of points of confidence index versus fraction correct, really once we get above, say 0.1, 0.2, generally this solution is going to be correct. So by filtering this out, we're removing the noise that can be captured during data collection due to overlapping grain boundaries or poor pattern quality or something. So using a partition to define a confidence index threshold and doing a confidence index standardization is a commonly used tool in OIM analysis. And there's a video that will explain that shortly.